All right, so now we're going to go over the interleaving distance and bottleneck distance in this video. So first, we're going to start out with interleavings of sublevel sets. So in this case, we're going to be looking at two sublevel sets. So we're going to be looking at two functions. So in this case, in this example here, f and g are just two functions from the reals to the reals. Right? These are just the usual function, the usual type of function you'd see in like a calculus class or algebra class. So in this case, our topological space X is just the reals. But it can be any more general topological space as well. Okay, so we can define something called the infinity norm between f and g here. So the infinity norm is just going to be the sup over all x in our space X of f of x of the distance between f of x and g of x. So formally, what this looks like is we're going to be looking for the largest vertical distance between the two graphs of these functions. So as x1 moves along this axis here, we want to look for the largest gap, right? The largest vertical gap between these two graphs here. And that's what's going to be the infinity norm. So let's say that the infinity norm between f and g is equal to epsilon. Then what we're going to have is that the sublevel set, so everything that maps at or below t is going to be contained inside the sublevel set of g for t plus epsilon. And we're also going to have the reverse containment as well. So the sublevel set for g at t is going to be contained inside the sublevel set for f at t plus epsilon. Now, we're not going to formally show this, but I'd encourage you to work this out as an exercise. It is a nice exercise to work out, and it's pretty straightforward. But yeah, we're not going to show this here. So these containments here lead us to the notion of interleaving. Okay, so now let's say we have, let's say we apply homology to the sublevel set filtrations of f and g, right? So we have all of these sublevel sets, and they're all contained, right? The sublevel set for f at t is going to be contained in the sublevel set for f at t prime whenever t is less than or equal to t prime. So we can do the same thing we did with filtrations earlier, is just apply homology, and we'll get persistence modules. So we're going to call the persistence module for f just vt, and the persistence module for g with wt. So, but yeah, we don't just have inclusions between the f's, right? We knew that if t was less than or equal to t prime, then f inverse of the interval from minus infinity to t would be contained inside f inverse of the interval from minus infinity to t prime. But because of what we said on the last slide, these inclusions here, we have these inclusions as well. And so we can apply homology to these inclusions. When we do that, we'll get linear maps, right? So we'll get a linear map, we'll call it phi t, from vt to wt plus epsilon. And we'll get linear maps going in the opposite direction as well, from psi t from wt to vt plus epsilon for each t in the reals. And these linear maps are going to satisfy certain properties as well. So, right, we actually get a string of inclusions here. So the sublevel set for f at t is going to be contained inside the sublevel set for g at t plus epsilon, and that is going to be contained inside the sublevel set for f at t plus 2 epsilon now. So these inclusions here imply that if we go via phi t and then psi t plus epsilon, we're going to get just the map from, let's see if I have a picture. well, okay, we'll get there. But right, remember zeta t plus 2 epsilon is just the map from vt to vt plus 2 epsilon. Right, so this is a natural map associated to the persistence module vt. And this condition here tells us that essentially we're sort of bouncing from vt to wt plus epsilon and then back to vt plus 2 epsilon. And this condition is telling us that that should be the same as just going straight from vt to vt plus 2 epsilon. And then similarly, we have the reverse inclusions as well, which give us this reverse commutativity condition here. So this one tells us that if we start at wt, and then we get a map from wt to vt plus epsilon, and then we get a map from vt plus epsilon to wt plus 2 epsilon. And what we want is that needs to be the same as just going straight from wt to wt plus 2 epsilon. Okay, and so we can actually isolate this condition, right? It's not important at all that we started with sublevel set filtrations. And so just like what we did with persistence modules, how we started with defining the persistence module of a filtration, and then define persistence modules. In general, we're going to do the same thing here, right? We can just isolate this algebraic condition, and we don't need the geometry at all here. So an epsilon interleaving between two persistence modules, VT and WT, is just going to consist of linear maps. So we're going to have phi t from VT to WT plus epsilon and psi t from WT to VT plus epsilon. And we're going to have these for all t in the reals. And what we want is that whenever t is less than or equal to t prime, we want this diagram here to commute. So this is exactly what this is saying, is that, right, we start at VT, and there are sort of two paths we can take. We can go straight from VT to VT plus 2 epsilon, or we could go from VT to WT plus epsilon, and then to VT plus 2 epsilon. And we want those two paths to be the same. Okay, then we also want the reverse one as well. So if we start at WT, then go to WT plus epsilon, or sorry, we start at WT, then go to VT plus epsilon. And then from VT plus epsilon to WT plus 2 epsilon. That should be the same as just going straight from WT to WT plus 2 epsilon. Okay, and then we also have these two conditions here. So these two conditions are telling us that basically that these maps phi t and psi t are just respecting the structure maps of our persistence modules in general. So we're not going to spend much time here, but we're not going to spend much time on this condition, but it is a condition that we have to assume. Okay, so now that we have this notion of interleavings, we can define a distance now. So this is going to be a distance on persistence modules, and the interleaving distance is defined as it's just going to be the nth overall epsilon, such that VT and WT are epsilon interleaved. So right, one thing you should always ask with distance is, what does it mean if the distance is 0? Well, in this case, if the interleaving distance is 0, assuming our persistence modules are nice enough, then a 0 interleaving is nothing. Well, if our persistence modules are nice enough, then the interleaving distance being 0 is the same, is equivalent to there being a 0 interleaving. And a 0 interleaving is nothing but an isomorphism between persistence modules. So that's very nice, right? It tells us that if two persistence modules are zero interleaved, that they're actually just isomorphic. So you can think about this interleaving condition as being a relaxation of isomorphism. Right? If they're zero, if they're isomorphic, the distance will be zero. But now that maybe they're not isomorphic, and the interleaving distance is sort of telling us how far apart are they from being isomorphic. Right, and so yeah, that's sort of the way you want to think about these interleavings, as like a loosening up of an isomorphism. Now, it is possible that two persistence modules might not have any interleavings between them. If this is the case, we just say that the interleaving distance is infinity. Okay, so now we've gone through interleavings. Now let's look at the distance we're going to use for persistence diagrams. So we used interleavings to give us a distance between persistence modules, but we want a corresponding distance between persistence diagrams as well, so that we can figure out when our two diagrams, like how far apart are two persistence diagrams. And this is going to be given by something called the bottleneck distance. And we're going to define this using matchings. And so the idea for matchings, you can see it here in this picture. So in this picture, there are two persistence diagrams shown. There's the one in blue, and then, or I guess it's like a dark blue, sort of purple, and then there's the one in pink. And the idea with matchings is it's actually pretty simple. It's much simpler than with interleavings. With matchings, we just want to match up these points in the persistence diagram. So we're going to match up, like if we look at this top leftmost pair, we want to match up those 2 points because they're close together. We can match up the other pair of points that are close together, but now we see that there are a bunch of different points in the blue diagram with no corresponding points on the pink diagram. What we can do is we'll just match them to the diagonal. So we'll see this more formally now. Right, so we can think of a persistence module as a multi-set of intervals. Remember, this was just the barcode decomposition. And so what we're going to do is we're going to include the diagonal, which is just the set of all intervals x comma x. So these are just intervals that are born and die immediately. Right? So you can think of this as representing like a feature that that just doesn't live at all in homology. And so we're going to include the diagonal with infinite multiplicity. So essentially in each persistence diagram, so in each barcode, essentially what this is doing is just, it's allowing us to match things to the diagonal for free. So if we go back to this picture here, you see that we really want to match all of these shortly lived blue points here to the diagonal. And counting the diagonal with infinite multiplicity is a way of allowing us to do that, right? Because we have, I mean, Hilbert's Hotel sort of tells us that if we have basically that infinity is the same thing as infinity plus 1, really. So like, okay, if the diagonal already had infinite multiplicity, or each point on the diagonal had infinite multiplicity, and now we want to match to add in 1 extra point to that, that's okay. We're not changing anything, right? If you have a hotel with infinite rooms, and every room is full, and then a guest wants to check in, is there room for that guest? And the answer is yes, right? You just take the person in the first room, move them to the second room. You take the person in the second room, move them to the third room. You take the person in the third room and move them to the fourth room, and so on and so on. And then the new person can check into the first room. So it's the same concept here, right? Essentially, the trick is that infinity is the same thing as infinity plus 1. Okay, so now we can define a matching between two persistence diagrams. So a matching is just going to be a bijection between the two multisets. And we can associate to each matching a cost. And so the cost of a matching is just, we're going to look at each pair of points, right? So this gamma we can think about as so gamma is going to be the function. Let's say it's going from the blue to the pink. So gamma is going to be the function that takes each blue point and maps it to a certain pink point here. And the cost, what the cost is going to be is we're just going to look at each blue point. Each blue point is going to get mapped. Each blue point is going to get mapped to some pink point. And we just want to look at what is the largest distance we have to go, right? What pair of blue and pink points that are matched together are the farthest apart? That is going to be the cost for this matching. Yeah, so formally it's this, right? So gamma is a bijection. And so we can think about gamma as just matching intervals in M with intervals in N. The cost of the matching is just, we're going to look at each interval I in M. That interval is going to get matched to some interval gamma of I. And we want to look at the distance between those two intervals, I and gamma of I. And then we're going to take the max over all such intervals, and that's going to be the cost. Okay, so now that we have matchings and costs of matchings, we can define the bottleneck distance. Yeah, so these matchings induce a distance called the bottleneck distance, just like interleavings induce the interleaving distance. So the bottleneck distance between two persistence diagrams, M and N, is just the inf over all gamma of the cost of gamma, where the infimum is taking over all matchings between M and N. So basically what we want is we want to find the best matching possible between M and N. And right, so like, let's go back to this picture here. Like I could pick a really stupid matching if I wanted, right? Like if we look at these 2 points that are sort of far away from the diagonal, or really it's 4 points, but 2 pairs of points, I could, instead of matching them to their sort of nearest neighbors, what I could have done instead is I could have matched this blue point all the way in the top left to the pink point that's closer to the diagonal. And then I could have matched the corresponding blue point to the pink point that's very far away from the diagonal. And that is a matching, right? We're still matching up points in each persistence diagram, but it's not a very good matching. We're moving things very far, and it's just, yeah, it's going to have a very high cost. So the idea with the bottleneck distance is we want to find the best matching, right? The matching with the lowest cost possible. And so that is the bottleneck distance here. And we can always, so if you give me any 2 persistence diagrams, I can always give you a matching between them. The reason for this is that we can always just match everything in the persistence diagrams to the diagonal. This is something we can always do. It might not be something that you want to do. It might be a very bad matching. Like if we look at this example again, yeah, I could match everything in here to the diagonal, but why? You know, it wouldn't be a very good matching at all. But anyhow, the point is that if you give me any 2 persistence diagrams at all, I can always find a matching between them. Yeah, and another thing is that because some of the intervals in our barcode decomposition can have possibly infinite endpoints, right? You can have features that are born but never die. A matching could have cost infinity, right? Like if you match a feature that was born but never dies to a feature that dies, you're sort of going to have to move that death point from infinity to a finite number, and that's going to give you a cost of infinity. So matchings might have infinite cost. And so because of this, that's okay, right? But a side effect of this is that the bottleneck distance could possibly be infinity. That's okay. That means we're going to have an extended metric instead of a regular metric. Okay, now we can get to the bottleneck stability theorem. So this is possibly the most important result in persistent homology. So what this says is that if we have two persistence modules, VT and WT, and let's say they have persistence diagrams M and N respectively, then the bottleneck distance between M and N is at most the interleaving distance between their two persistence modules. Right, and so this is a very, very important result for persistence. It tells us that this act of starting with the filtration and going to a persistence diagram is stable. This so like in the real world with data sets, there's always going to be some amount of noise present. It's just a fact with real world data. There's always some amount of noise. And the bottleneck stability theorem tells us that persistence diagrams are not sensitive to this noise, right? Like, let's say we have some noise that changes our data set by like epsilon. Well, that let's say the noise shifts our data set by epsilon or something. What that tells us is that our persistence diagrams are going to be shifted by at most epsilon anyway. So it's a very important result. What you don't want in statistics is like a sort of invariant that changes wildly with just small changes of your data and stuff. And this is telling us that this is not the case for persistence. The barcodes or persistence diagrams are stable invariant. Now this bottleneck stability theorem on the last slide can actually be strengthened a bit into something called the isometry theorem. And so what this says is that not only are the bottleneck distance and not only is the bottleneck distance less than or equal to the interleaving distance, actually the two distances are equal. This is sort of surprising. So this is stronger than the bottleneck stability theorem. And it implies that basically the extended metric space of persistence modules and the extended metric space of persistence diagrams are actually isometric. So this is a very nice result. It's sort of, right, the bottleneck stability theorem is one half of this result. The other side of it is showing that, right, so the bottleneck stability theorem, there's a less than or equal to here. So to get the isometry theorem from this, you'd have to prove the opposite inequality as well. It turns out the bottleneck stability theorem, this one here is the hard direction. But yeah, this one is a bit stronger and a very nice result.